Right, the 2014 Geometry External, question 3. This is quite a long one, so we'll see whether we can get it all in one video or not. You can read the question. 2 reasons that Ahmed must have made a mistake. Well, clearly this angle here does not look like 70 degrees. 70 degrees is an acute angle, less than 90, and this angle here is clearly more than 90. It is drawn to scale, so if you have a protractor you could check that. In fact, you could check all 4 angles with your protractor. This probably looks 90, and this is very close to 90 but still acute, and 73 is acute, less than 90, so this is clearly the mistake. So one reason is that he measured the 70 degree angle incorrectly. The angle is clearly obtuse, which is greater than 90. Now the second reason that we know Ahmed made a mistake is because if you add up these 4 angles, 70 plus 87, it comes to a total of 320, and angles in a quadrilateral must add to 360. However, angles in a quad should sum 360 degrees. Explain what mistake Ahmed might have made in using his protractor. If you know or have ever tried measuring angles with a protractor, you'll remember that when you're reading around the angles, there are usually 2 sets of degrees. There is a set that starts from 0 and goes around to 180, and then on the other outside they might start from 0 that way and come back to 180 this way. So chances are when Ahmed was measuring this angle, while he thought it was 70 going this way, he should have been reading from 0 and reading round, which would make it 110, because 70 plus 110 is 80. He might have looked at the wrong side of the scale and read 70 degrees instead of. The other thing you could do to check is if you added 110 to the other numbers, you'll see that you do in fact get 360 degrees. And of course you could use your protractor as well if you've got one and go up and measure that. Right, another brightly coloured picture. This time it's about tessellations. 6 copies. You can pause and read the question if you like. Why it is true that any quadrilateral will tessellate. You may wish to refer to the labelled diagram below or to the tessellation above. Well, if we do a combination of both, because this is a quadrilateral, I know that angle Q plus U plus A plus angle D must add to 360 degrees, because that's angles in a quad sum 360. Now for a shape to tessellate, and I'm going to write over here, but you can write down below. For a shape to tessellate, it's really important that angles around a point sum 360 degrees with no gaps. So as you can see here, where 4 of the shapes join around this point here, we need to make sure that the angles on each shape around the point are going to sum to 360 degrees. So looking at the shapes, this here is clearly a Q angle. This is the other end, which is clearly an A. This is the big one on the inside, the U. It's just been turned upside down, but that's definitely the same measurement. And here, of course, is the measurement for the D. So around this point I've got an angle U plus an A plus a D plus a Q. And what do I know about those four angles? They sum to 360. Notice that at point, we'll label it point O, the four angles are Q plus U plus A plus D, which do add to 360 with no gaps. And obviously this is going to be true for any quadrilateral, will have the same property. If you want a bit of an explanation to carry on, although that's probably enough, any quad will have this property. So for example, if we draw another strange shaped quadrilateral, A, B, C, D, I know that A plus B plus C plus D adds to 360 degrees, and I could put them all together around a point. We could have an angle A around this point, and then we could put a D. We could put turn the shape round so that B is touching in there, and lastly we could turn the shape around so that the C is touching there, and they'll go around a point with no gaps. So there would be no gaps and the shape will tessellate. Right, next page. This is a long question. Here's another shape. It's a pentagon, so we're drawing in external angles. You can pause and read the question if you like. And now we have a bit of a problem with our external angle on that one. Works out the size of the angle C is shown below. Give the geometric reason for his calculation. The reason is because exterior angles of a polygon sum 360 degrees, and it doesn't matter how many sides there are. Explain the meaning of the negative measurement of the angle C and state when this will occur. Well, obviously it's going to occur when your polygon has what we call a concave polygon, so that one of the angles goes inside, appears to go inside the polygon. Most polygons, of course, if it was a pentagon, would look like that, and we call that convex. And then all of the exterior angles around the outside would sum to 360. But because they've taken two of the sides and gone in to make it a concave polygon, then we have this anomaly happening. So obviously this is going to happen, this will occur for a concave polygon when one of the angles is inside the polygon. If you don't remember the word concave, you could explain it. Angle C is clearly, obviously, positive 106. The negative 106 shows that this exterior angle is inside the shape. Right, and last page. Angle EGR. EGR, we might call that an A. Plus angle GRA, we might call that B. equal 180. They sum to 180. So if the two of them add to 180, then we can assume that that side and that side are parallel, because we have co-interior angles adding to 180. So proving that line GE and RA are parallel, because co-interior angles in parallel lines are equal. So GE and RA are parallel. Prove that angle APE, which is labelled W up the top here, APE equals angle PAR, so we want to prove it equals that one, plus angle PEG, PEG plus that one. If we call that C and that D. Now the trick to use for these sort of diagrams is to put a third parallel line running through, and then it's easy to see that this angle here is alternate to this one, which will equal D, and this angle here is alternate to that, which will equal C. But we need to be able to put that in writing. So putting in the parallel line here, we need to call it something. Let's see what letters we've got. We haven't used X and Y, so we'll call it X and Y, which means that angle EPY is going to be the same as angle PEG. So angle PEG equals angle EPY. EPY, which we've called D in the diagram, and angle RAP, PAR they call it. It's a bit tricky. Equals APY. We've called it C. Now W is made up of EPY plus this one in here, APY. So W equals, now EPY is the same as PEG, and APY is the same as PAR. So we've just proved that W equals that one plus that one. We need to explain, so we need alternate angles in parallel lines are equal, and similarly with this one.